In this lecture, we will be doing some numericals. So this is lecture 10 of Unit 1 Quantum Mechanics. And before we really go on to the numericals, we got to recollect what are the various formulas we have come across in Unit 1. The first thing we have seen that we have the formula for energy E is equal to h nu or E is equal to h instead of nu you can write it as C by lambda. Also, we have seen the de Broglie concept of matter waves, wherein the general formula for lambda is equal to h by p, where p is equal to mv. And for a photon, p is equal to mc. The reason is photons travel with the velocity of light. For an electron, the formula for lambda was lambda is equal to 12.27 under root of V, where V is the potential under which the electron moves, and the units are in angstroms. We also seen a formula for lambda in terms of kinetic energy, where lambda is equal to h under root of 2me, where E is the kinetic energy of the particle. When we came to particle in a one-dimension box, we got an expression for energy of the free particle, which is equal to E is equal to n square h square by 8m a square. Keeping all these formulas in mind, we can apply these in situations and understand the concepts. Now, the first numerical which we can see is calculate the wavelength associated with an electron raised to a potential of 1600 volts. So while doing a problem, always first write down what are the parameters that are given. So given over here is the potential V, which is equal to 1600 volt. And we know that the formula by which we can calculate lambda is equal to 12.27 under root of V, the units being in angstroms. Substitute the value of V over here. From this we can calculate lambda is equal to 0.31 angstroms. What is the concept you have learned from this formula? We know that electrons are particle in nature, but when they move under a potential or when they have kinetic energy, they also behave like a wave. And in this example, we are able to calculate the wavelength of electrons, which is equal to 0.31 angstroms. Next, we can see the next problem. Calculate the de Broglie wavelength of a proton whose kinetic energy is 1 into 10 to the power of 6 electron volt, given mass of proton is 1.67 into 10 to the power of minus 27 kg. So once again, what is given over here? Kinetic energy, we take it as E is equal to 1 into 10 to the power of 6 electron volt. We have to convert electron volts into joules. So we multiply this with charge of an electron, which is 1.6 into 10 to the power of minus 19 joules. Planck's constant h is equal to 6.626 into 10 to the power of minus 34 joule second. And also given is mass of the proton small m, which is equal to 1.67 into 10 to the power of minus 27 kg. What is the formula we can use over here? Lambda is equal to h under root of 2me. On substitution, you can see that lambda is equal to 2.86 into 10 to the power of minus 14 meter. Meter is the unit of wavelength. So from this, we can also see that a proton also has got a dualistic behavior, that is particle nature as well as a wave nature. Thirdly, we shall see calculate the velocity and kinetic energy of an electron of wavelength 1.66 into 10 to the power of minus 10 meter. Given wavelength of the electron is 1.66 into 10 to the power of minus 10 meter. We know the value of Planck's constant, h is equal to 6.626 into 10 to the power of minus 34 joule second. Mass of the electron m is 9.1 into 10 to the power of minus 31 kg. Now what is the formula we can use over here? We know that lambda is equal to h by mv. Lambda value is given and we know the value of h and m. From this we can calculate the velocity. On calculation you can see velocity is equal to 4.386 into 10 to the power 7 meter per second. Second thing that is asked is over here is kinetic energy. General formula for kinetic energy is half mv square. We know m value and we have calculated the value of velocity. On substitution, we can get the value of kinetic energy as 54.5 electron volts, which can be converted into joules. At this point, think of another formula from which you can calculate the kinetic energy from the concepts that we have learned. If you remember, we have got lambda is equal to h under root of 2me, where capital E is the kinetic energy. So we can calculate the value of kinetic energy from that equation also. So I hope you will work it out and check out. Compare the results obtained from the general formula for kinetic energy half mv square and from the relation lambda is equal to h under root of 2me. Now the fourth problem. Calculate the minimum energy that an electron can possess in an infinitely deep one-dimensional potential well of width 4 nanometer. So given is the width is equal to 4 into 4 nanometer. So it is 4 into 10 to the power of minus 9 meter. And we take n is equal to 1 because it's the minimum energy. What is the formula? We know E is equal to n square h square by 8m a square. N is equal to 1. We already seen what is the value of Planck's constant. Okay. Then we also know the mass of the electron. Okay. Over here, a value is 4 into 10 to the power of minus 9 meter. On substitution, you will see the answer as E is equal to 0.03769 into 10 to the power of minus 19 joules. Here we have made an attempt to convert joules into electron volts. Okay. And the answer over here is in electron volts, E is equal to 0.0235 electron volts. So this is the concept we have learned in particle in a one dimension box, wherein we can find out the energy of the particles. The fifth one we can see is the wavelength of yellow light is 5890 angstroms. What is the energy of the photon in the beam? Given wavelength is 5890 angstroms, which can be written as 5890 into 10 to the power of minus 10 meter. Formula we have seen is E is equal to h nu, or nu can be written as c by lambda. Okay. C over here is the velocity of light, which is 3 into 10 to the power of 8 meter per second. The reason is photons travel with the velocity of light. So on substitution, you will get the value of energy E is equal to 2.11 electron volts.